All right. So first of all, this is going to be our last lecture until Friday, since Wednesday is a school holiday. So my goal, and I don't think we'll have any problems meeting this, is to get to the end of homework number 4 and exam 1 material by the end of today. So sometime at the end of today's lecture, if not before, I'll tell you to draw a line in your notes that this is the cutoff for homework 4 and exam 1 stuff, and you don't need to look at anything below that line when you're preparing. So then we don't have lab this Wednesday. We'll of course continue, life goes on Friday, but this will put everything in your hands so you can prepare for the exam, which is a week from Wednesday. So since we're not meeting lab this week, we'll meet lab next week. So that exam is, again, it's held during your lab period, but due to the high enrollment, I have secured rooms elsewhere. So please make sure you look at the exam logistics so you know where you are going. The 2 different lab sections have different rooms. I just couldn't secure the same room for such a large block of time. So if you ask your friend in the other lab, make sure you realize that they may have a different place they need to be going. Also, for those of you that did not finish the problem session from last week, the general rule is that you are allowed to turn it in up to the next lab meeting, and that excludes exams, so next non-exam lab meeting. So that means we don't meet this week, you have your exam next week, so you can give it to me even as late as the following Wednesday for credit. However, I strongly discourage that because that's obviously material that's covered on your first exam. So you want to make sure you know what you're doing with that stuff before the exam, not a week after, okay? So I would strongly encourage you to come by office hours and make sure that you're checked off for that, and more importantly, that you have the answers correctly, because those are very much the type of things you might see on the exam, okay? Any administrative or logistical questions before we get started? All right, so let's finish the Gauss's law with cylindrical symmetry. Here we go. Gauss's law as always, and then in this case, our catcher is a cylinder. And the cylinder, the area is going to be the area of the curved side. There is, of course, also 2 end caps, but as we showed last time, those end caps contribute 0 flux because the normal and the electric field are 90 degrees to each other. And then we showed that this can very quickly give us the electric field of a line charge. So let's go ahead now and start doing the stuff that we couldn't do. We already knew the electric field of a uniform line charge. It's nice to be able to get it much more quickly, but we want always Gauss's law to produce something that we couldn't have gotten easily otherwise. So let's go ahead and do the uniformly charged cylinder. It's going to be infinitely long, something like this. So this is the infinite cylinder with uniform charge density, okay? So you can again make symmetry arguments that this should be exactly identical to every radial direction, so on and so forth. You can draw that all along down the thing, and we'll go ahead and put our Gaussian surface in there. Let's go ahead and put it outside at first. A little bit better drawing than I did last time, like so. Remember, it is a closed surface. It does have 2 end caps. Even while the end caps don't contribute flux, make sure you understand that for Gauss's law, it does have to be a closed surface. It has to trap charge inside. And don't confuse the lowercase r, which is my Gaussian surface, that's where I ultimately want to end up knowing the electric field. Don't confuse that with the dimension of the object itself. So I'll use capital R for that. So let's go ahead and do it. And then for the Q enclosed, I'm just going to put uniform charge density times the volume enclosed. So you might say, isn't the volume of this whole infinite cylinder infinite? Yes, it is, but not the part that's trapped inside. Okay? So this Gaussian surface has a length L, and that's going to inform how much we've trapped inside. So the volume of a cylinder, well, of course, the cross-section is pi r squared, and then we just have to multiply it by L. Okay? So it's just a circle that's kind of dragged out, right? Pi r squared times L. And that is the big R, because how much do I have trapped inside? Well, of course, I don't have charge all the way to the edge of the Gaussian surface. The charge stops at capital R. Any other questions? Okay, that was your question? Okay. So that's really all you have to do in Gauss's law. Okay, you have to keep track of which R you're talking about. Just to give you a roadmap, this is always your Gaussian surface. Left-hand side, always a Gaussian surface. Over here, if you're outside, so your R is bigger than R, then this is like this, right? The charge actually runs out before you get to the edge of your Gaussian surface. The only thing I'm going to do different is inside, is I'm going to change that to lowercase r, okay? And of course, I don't enclose all the charge, I just enclose what's up to my Gaussian surface. So that's really all you have to do, is you have to decide on the right-hand side, is it big R or small r? It's big R if you're outside, it's small r if you're still inside. Does that make sense? That's the only decision you have to make. Right-hand side, is it this or is it this, okay? All right. So let's go ahead and knock it out. I guess let me recopy it nicely first. And this is important. You've done something wrong if this doesn't happen. The L's have to cancel. The reason why is that L is just the length of your arbitrary testing surface. It would be really weird if the field depended on it. Okay? So that's got to get out of there. Okay? What else? We can cancel off the pi's. And that's, after that, we're pretty much all set. And as usual, I'll copy the active ingredient out here. Now it's proportional to 1 over r, and that should be a strong clue that, of course, this behaves just like a line charge when you're outside it. So you guys remember when we were talking about the spherical geometry, that as soon as you're outside of a sphere, immediately, not just far away, but immediately the electric field is indistinguishable from a point charge, right? Remember we talked about that? That's a huge shortcut. Well, that's the same thing here. As soon as you're outside of the cylinder, it collapses onto the field of a line charge, okay? So when you're outside, let's just make a little chart. When you're outside a solid sphere, or I should even say solid sphere, I should say sphere with a radially symmetric charge distribution, it immediately collapses onto a point charge. And when you have a cylinder, also with radially symmetric charge density, it immediately collapses onto a line charge. that's the secret, is that when you're outside these charge distributions, you almost don't even need to bother. In fact, let me show you, indeed, that this is exactly the formula for a line charge. Not just has the right proportionality, but literally is the exact formula. Now what I'm going to do there is I'm going to take this pi that I just canceled, and I'm going to add it back here. Hopefully that doesn't bother anybody. I can add whatever that I want, because if I introduce it to the numerator or denominator. Well, this thing right here, rho times pi r squared, what this is, it's the charge per unit volume, right, that's what rho is, times the cross-sectional area, right, that's what pi r squared is, it's the cross-sectional area. So if I take the charge per unit volume and I multiply in the charge per area, this is the effective charge per unit length. So it's how much charge is carried per unit length along this thing. So if we neglect the fact that charge is, of course, distributed radially as well, and we just say how much charge do we get, we're thinking of it as a bunch of slices, and those slices extend a distance L, right? It's like sliced bread, right? So what we're doing is we're taking the charge per unit volume, we're multiplying in the area of each slice of this bread, right? Sliced bread, yes? Mm-hmm. Okay. Or like when you're making cookies, you know, the tube. You guys
Yes,
know?
sir.
Okay.
Yes, sir.
So charge per unit volume, and I multiply in the area, and then I just leave out the length because I want to express it as charge per length. So if you do that, what do you get? You get the exact formula for a line charge. The only difference is that lambda, which is the charge per length, of course, already folds in some of the substructure of the phase, right? Because now the charge isn't just along a line. So you have to multiply in each slice here to be able to talk about the effective charge per unit length. So there we have it. Old news, okay? So let's go ahead and start our graphs like usual, and go ahead and then move on to the inside. So we'll make a graph of the radial component of the electric field. In this case, remember, this is not the magnitude of the field, this is the radial component. So it'll be positive for positive charges, so it'll be radially outward. It'll be negative if it's a negative charge, but I don't have that. So here we go. Looks something like that. The moment you get outside, it's identical to a collapses onto a line charge. You can, of course, graph the voltage here as well. While the electric field points radially away, so electric field points towards lower voltage, so I know the voltage drops. This is where I get to remind you about, you've explored this system before, at least the line charge. That was the end of homework 3 somewhere. And of course, when you integrate 1 over r, you get what?
ln.
ln. And ln does not have an asymptote, so no matter how hard you try, you can't keep it above. So it's going to look something like this, right? No matter how hard you try, at some point it will go negative. So this is proportional to negative ln r. So voltage drops, and at some point it's going to drop to 0 if you set 0 out there somewhere, and then it's going to keep dropping, and that's kind of it. Okay. Are there any questions on that before I move on to the inside? Okay, so here there's no obvious place to set 0. You might just want to set v equals 0 at some point, wherever you feel like it. Okay? Let's do the inside. So I'm just going to use my same sketch, try to clear this out. I'm not just doing this to be annoying, because you can't erase like this on your paper. I don't recommend that you do. But I do want to point out it's the same underlying charge configuration. Nothing's changed about what I'm looking at. I'm just putting my testing surface in a different place, right? I'm just saying, now I want to know what the field is here. So I put my cylinder inside.
Quick question.
Yeah.
For conductive?
It's definitely not conductive because conductor all the charges on the surface, right?
Okay.
So if this is uniform charge density, this has been a very specially prepared insulator where someone has gone with a tiny pair of magical tweezers and taken charge off everywhere in the interior. I don't know how they reached into the interior to do this, but this is just a construct. So again, what's the only difference is that now I'm not enclosing all the charge. I'm just enclosing the charge that I've enclosed, right? So I just switched this, right, to the lowercase r. I can only count the charge that I've actually trapped inside there, right? All this stuff. Does that make sense?
Yeah, so both r's are the same now, right?
That's right. And it's the math is gonna result very differently because there's gonna be some cancellation because my testing surface is the same as the radius that encloses charge. So now, basically, all I do is I swap out lowercase r. The L's still cancel, that's important. If you don't, you did something wrong because that'd be weird. Why does your electric field depend on your testing surface? And then everything else, the pi's still cancel, but now we do have that this r cancels with one of these, and we get rho r over 2 epsilon naught. And again, let me put the constants in a group and looks like that. So now the electric field grows linearly with r. That was the same result that we saw in the sphere. When you're inside, it grows. So let me sketch it. Looks like this. And you can confirm from both the inside and outside formulas that they do agree on the surface. If you evaluate either one of them right at the surface, you will get the same value. Okay? And again, if you don't remember the reasoning for why this makes sense, the electric field is 0 right at the middle, because if you put a charge right at the middle, of course, it will be influenced from all around equally, right? But then if you put some kind of little tunnel here for it to burrow through so it can move unobstructed, the moment you place it a little bit off center, there'll be more charge to one side than the other, which will cause a sort of a net push. And that net push will increase more and more and more until it gets to the surface. When this charge gets to the surface, now all of the charge is to one side. That's the largest push you're ever going to experience. That's the largest field you're going to ever experience. And then from there, if you move out into the confines, out of the confines of the cylinder into free space, you'll be putting some distance between you and this cylinder, right? So the electric field will be dropping. Are there any questions on that? Okay, and then this, by the way, is almost identical to the sphere. I think there was a factor of 3 here instead of a factor of 2. We basically already did this. Let me show you how this looks.
Constant.
It's when we integrate, it's an upside down parabola. The slope here is 0. Why? Because
Electric field.
the electric field is 0. The slope here is maximum. why the electric field is maximum. In fact, the slope here is just, remember, the negative of the electric field. Then we know that the slope will decrease because the electric field decreases. Remember that the electric field is just the negative slope of this graph. So there we have it. So the electric field is always positive, so that's radially away. So it'll get pushed always radially away. First, it'll grow in strength, the amount of force you'd experience from on a positive charge, then it diminishes. And if you want to think of this as like your skateboard ramp, it would be a gradual decrease in voltage. So it would gradually speed up at first, then it would plunge, speed up a lot right here, and then, of course, ease off again, okay? So there we have it. Are there any questions on that? Okay, so it's very similar, as hopefully you can see, it's very similar to the sphere, just a slightly different stuff that you put here. It's a different area of your catcher because it's a cylinder instead of a sphere. And then over here, of course, your volume is slightly different. But other than that, the process is the same. You can also, of course, do the conductor where all the charge is on the surface. I'll skip that. Leave you some fun for, trying out on your own. It's pretty much the same deal. And finally, let's just talk about what if it's a radial function. So it's a function of radius only. Still has to be radially symmetric, so this is the only way that you can have it. So then, what would you do for Q enclosed? You'd have to integrate. You'd perhaps start at r equals 0, unless there was a hole in it. And then here, you would either go to r or capital R. It really depends. If you're inside, you should stop when your Gaussian surface runs out, or if you're outside, don't keep integrating past where you have charge, right? That's really the only decision you have to make. Which R? Your dV, as always, if we draw in this cylinder, our dV, because it's radially symmetric, is going to be made out of these concentric shells that look like this. We want to know what's their area and then multiply them by the thickness. So this is my dV, and each of these shells has a little thickness. Each shell can have its own local density. So we talked about a non-uniform density, so the shells closer in, they have a different charge density than the shells further out. And A here, of course, that's the surface area of this thing, so A is going to be 2 pi r times L. So if you break this into a sheet, this sheet has one dimension, which is the circumference, and of course the other dimension is just the length, and then you're off and running, okay? So how do you do this? Integral of rho times 2 pi r L dr. So that's your volume element. Your dV equals A times dr. So, presumably, the only reason you're doing this is because rho itself is a function of r. Don't forget that you have an extra r here that you need to integrate with it. So that's the common mistake. The rest you can, of course, factor out. They're constants. And, as always, I want to convince you that if you are doing this by accident, because rho is really a constant, so if rho is actually constant, you can factor that out, along with, of course, 2 pi L, which is always constant. And then you get r dr. What's the integral of r dr?
R squared over 2.
R squared over 2. So what do we get? Rho times 2 pi L times r squared over 2. The 2's cancel. I get rho times pi r squared L, which is, of course, the volume. So I'm back to what I know I should have been doing in the first place, just rho times v. If your charge density is constant, why are you integrating? Just multiply rho times v. Okay? So, as far as how I got these things, you don't need to memorize them. I know for some of you that you may not be as comfortable with them. They're all on the equation sheet. Just grab them. If you don't remember which one is which, it's real easy. The one with L is a cylinder. Okay? That's it. Are there any questions on that? All right, so final order of business. I guess before I do that, let me catalog my results real quick. This might be a good exercise.
Sure.
So I know that point charges drop off, their electric field is 1 over r squared. So this is for point charges. And let me remind you that this also applies to any finite charge, so non-zero charge when you're far away. And it applies to all radially symmetric spherical stuff right away, immediately. So if you have a radially symmetric spherical charge configuration, you don't have to wait till you're very far away for it to look like a point charge. It is collapses immediately to that. Okay? Then we looked at line charges. They drop off as 1 over r. This is for a line charge, an infinite line charge, and any radially symmetric cylindrical thing right away. So radially symmetric cylindrical immediately.
Professor?
Yeah.
Would we have anything but radially symmetrical cylinder?
No, because that requires much more advanced mathematics.
That's right.
If you can't count on the fact that the field is going to be only radial, if it's somehow going to have some stronger on the right versus the left, that's way harder.
Mm-hmm.
You take whole classes in how to handle those geometries. You learn about Bessel functions and spherical harmonics and all sorts of crazy stuff to handle those. Radially symmetric only for us. Okay. So what we found was we extended one dimension to infinity, right? A line charge is one infinite dimension. So it took an r out of the denominator. So we went from r squared to r in the denominator. Then
an infinite plane.
We took a second dimension to infinity, right? And we found out that that took another r out of the denominator, and that was constant. So that was constant for when we had an infinite plane of charge. So now we have a two-dimensional surface. Well, why am I bringing this up now? This is mostly old news. Well, we just added a third dimension. We found that both inside the sphere and the cylinder, the electric field actually grows as r. So it's like every dimension that you extend takes an r and adds an r in the numerator. So this is proportional to r that is inside a sphere or cylinder. And again, remember this has to be radially symmetric. So that's just kind of a catalog of stepping up from a point, which is 0 dimensions, to a line, which is 1D, to a plane, which is 2D, to full volume inside a full volume is 3D.
Okay.
So you can see that each dimension basically folds in an extra R. Okay?
That's fine.
All right. Now, let me say a few brief words on what you would do if you don't have radial symmetry. So, no radial symmetry. Well, you've got issues, okay? Here's an example. I think your homework is something like this. This thing has a hole, but the hole is more toward the right than the left. So this doesn't pass what I call the curtain test. If I put the curtain over this and I twisted it, you could easily tell because the hole is going to have migrated, right?
Mm-hmm.
Well, here's the beauty, is that if you can make the charge configuration by a superposition of simpler charge configurations, you can also, the electric field will be the superposition of those of the simpler charge configurations.
It's not fun.
So if you can concoct
So
this weird shape with an off-center hole, and you can somehow get it by making it up from two different charge configurations that are simpler or more, then you can also get to superimpose the fields of them and you're done. So let me tell you how to do that here. So, for instance, let's say you want to know the electric field right here. Well, you could think of this as a solid thing without a hole. And of course, you could calculate how much electric field it contributed to that point. And then you could put on top of it a smaller sphere with negative charge density, and that would of course contribute like this, radially inward. But guess what? In that region where the charge densities are equal and opposite, that is equivalent to a hole, right? Does that make sense?
Yeah, I see it.
So when you have a region
It cancels out, so.
where you have both positive and negative charge density, that's equivalent to a hole. So if you can make the charge configuration based on things you know, you can also calculate the electric field as a superposition of those contributors. Okay? So that's a really handy trick. When all else is lost, or you just want to avoid some nasty integration, what you can do is try to concoct the charge configuration out of simpler charge configurations that you can calculate the fields of. And if you can make the charge configuration by superposition, you can also then find the electric field with superposition.
So are you saying in that hole, because we know the charge density there in the whole thing is uniform, all we have to do is just take the negative of that and multiply by the area of that hole, and then we flip the sign?
I've talked extensively about what you would need to do to get the electric field of a, say,
Of
a
the
sphere
whole
or
thing.
something.
Okay,
So,
I see.
yeah, but I am assuming that this is the same positive charge density as this is negative charge density, because otherwise that wouldn't be equivalent to a hole. Okay, so in the remaining, so that's just a trick. Be on the lookout for that trick. It's a really handy trick. In the remaining 15 minutes, there is a couple other problems on the homework that I want to touch upon. So let me remind you that we've been talking about is if you apply an external electric field to a conductor, minus, 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 plus, 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 we have found
Perfect
by
choice.
conceptual means that that there is perfect shielding within the interior, right?
Mm-hmm.
Now, one of the conspicuous things that you may have noticed is that I never ask you to calculate how much charge, and that's because in general it is a very difficult calculation. To figure out exactly how the charge distributes, exactly how the charge polarizes to make that shielding happen. It's like musical chairs, they generally find their spots to cancel off the field inside, and they'll try out a bunch of stuff, and if that doesn't cancel the field inside, they'll just move until it is. There is one exception, however, where we can calculate the exact amount of charge polarization, okay? So there's one very narrow case, okay? So generally, we do this concept only because it's difficult to calculate the amount and the distribution of the charge polarization until E net inside goes to 0. But there's one exception. So let me tell you what that exception is. That is when I can do the whole thing with perfect spherical symmetry. So let me draw this for you. This right here is going to be a positive point charge. We of course know that its electric field goes like this. And this is going to be the cause of my E external. So then the neutral conductor, I guess I should have labeled it over here, neutral conductor that is going to get charge polarized is going to be in an unusual place. It's not going to be to the side of this point charge, it's actually going to be all around it. It's going to look like this. So it's going to be a hollow thing. And I know this is confusing. Where is the material and where is it not? So I'm going to try to very gently shade it. This is the material. This is my conducting material. All right? So that is a neutral conductor. So, ironically, the quote-unquote external electric field, yes, it's external to the material of the conductor, but what's causing the quote-unquote external field is actually a point charge trapped inside a cavity inside the neutral conductor. So when I say external field, it's of course external to the material, but it's actually trapped inside a hole in there, okay? So, what's going to happen? Well, let's draw the charge distribution. Of course, the interior of a conductor always needs to be shielded. So just like over here, the minus charges moved upstream and the plus charges were downstream, that's the same thing here. So minus charges will actually get drawn to the inside. They follow the external to the material. They follow the external field upstream. And then, of course, the positives get as far away from there as they can, and those will be to the outside. So there's my charge polarization. It looks something like that. So now, instead of a left versus right charge polarization, it's an inside to outside charge polarization. It's an inner surface to outer surface. That's simply due to the placement of the charge. Okay? So, let me go ahead and figure out what happens. In fact, I should have probably color-coded this. Let me code these as positives, as red, so I can talk about the negatives and positives separately. So, this will cause the net electric field here in the interior of the conductor to be 0. How do I know that? Well, if it wasn't, then there would be more charge polarization till it was. So, How does that happen? Well, if we, for instance, put a Gaussian surface like this, and we test how it is possible that the net field is zero, even despite perfect radial symmetry, we have to conclude that how much charge is enclosed. So if we have perfect radial symmetry, so if E is zero, what does that have to mean about Q? Zero. So at that point, we have to have zero enclosed charge. Well, how is that possible? It means that whatever positive charge is sitting in the middle of the cavity, an exact amount of that minus charge is drawn to the inner surface. So we've just been able to deduce exactly how much charge polarizes. Well, exactly that same amount. I can actually draw the electric field of this negative charge. It's negative, it points radially inward, so it looks something like this. We did this a couple lectures ago. We have charge that rests on a spherical surface. So we know the net field is zero inside of that, considering just the green charge. But then outside it picks up, right? So what we have in here, notice that we have that the point charge contributes radially away, but the negative charge is radially towards. That's exactly how it cancels, right? Does that make sense? Because we know that once we get outside, this negative shell of point charge, it collapses, right? So this plus this minus, 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 minus. Once you're outside of that, it looks like plus, plus, minus. It's just like putting a negative point charge on top of the positive point charge. Remember, once you're outside a spherically symmetric charge, it collapses immediately onto a point charge. That's what allows us to figure out how the electric field is zero inside and how much charge is needed to polarize onto the inner surface to make that happen. So let's make a sketch. So the electric field, if we make a sketch of this, let's label, I guess, the radii here. So let me label the inner radius A and the outer radius B, I guess. I don't know why, but I am. So here's what happens. The electric field of a point charge goes as 1 over r squared, like that, falling off there. And of course, when I'm inside my Q enclosed, let me put it on the side here, Q enclosed. At this point, I've only enclosed the point charge. Then the electric field goes shrunk, like this, goes to 0, because I'm inside the body of the conductor. The Q enclosed is 0. Again, how did that arise? It's because you have the plus Q from the actual point charge, and then you have the minus Q from the negative half of the charge polarization. So we have that in the body of the material itself, you're shielded. That's what the charge polarization is for. Okay? Now let me point out that it actually, the black field from the point charge and the green field from the inner half of the charge polarization don't just cancel in the body of the material, they cancel forever, okay? So they cancel outside, not just from A to B, but from A to infinity. They will cancel each other.
Isn't it because they're limited strength?
Well, again, they're not both 0, but they cancel with each other, right? And they cancel not just here, but here as well, right?
Yeah, I see.
So is the electric field 0 to forever? Well, no, remember, because if we go outside this whole thing, now we're going to enclose the positive charge. We're going to enclose the positive half of the charge configuration. So that, when you're inside, it doesn't matter, but when you're outside, it picks up. So it looks like this. So as soon as you get outside of that, that collapses to a point charge. And what does that look like? It looks like this. When you get outside of B, the amount of charge enclosed is plus Q again. Because of course, if this truly is a neutral conductor, if you pulled minus Q to the inner surface, if the whole thing is going to be neutral, there must be plus Q on the outer surface, right? So there is plus Q on the outer surface. And so, ironically, as soon as you get outside the whole thing, it collapses onto a point charge. In fact, if I can draw correctly, which it looks like I can't, it should pick up right where it left off. So it literally looks like a point charge. It's interrupted by the shielding, and then it picks up right where it left off. So again, think of that Gaussian surface getting bigger. Here it encloses Q.
Okay.
When you get inside the material, it closes 0 because it's Q plus minus Q. And then when you get outside, it goes back to Q because it's Q plus minus Q plus Q, right? Now, what have you done here? You've essentially just transmitted information about what's enclosed, right? Plus Q is enclosed inside a neutral conductor, and information about that is transmitted to the outside world. So the charge polarization happens, and it protects the interior of the material from a field, but information about that charge is ultimately passed on. You can tell what's in the outside world, what's in there, by looking at the field. Okay? If you have no idea what was inside the cavity, you can nonetheless look at the charge on the surface and look at the field that it's making and say, I know what's in there. However, this is made ultimately by this positive red charge. That's what's creating it. So here's one of the cool things we can do. You guys remember, we could ground this, right? And we could cancel off this charge polarization. You remember that?
Yeah, let all the electrons.
We can do that here. So that always cancels off the charge polarization on the far side, right? So we can cancel off the red charge.
Which means 0? No, this means it's negative.
It means that that is overall charge negative. It's like we're charging this by induction, right? You guys remember that?
Yeah.
Now that creates a cool situation over here because remember, what was ultimately transmitting the information about what was inside the cavity was actually the charge on the outer surface. Now it would look like this. So now it would extend the field that was shielded, not just to the material itself, but to the entirety of the outside world. You have now made it impossible for the outside world to tell that there's a charge inside the cavity. You have shielded it from the rest of the universe, okay? So you have this positive charge lives inside this cavity. An equal amount of minus charge got drawn to the inner surface and essentially shields the rest of the universe from that field. And then there is no plus charge to then pass forward the information that there's something going on in there. So you can actually shield the rest of the universe from knowledge of a charge by putting it into a grounded a grounded conductor. Put it inside a cavity in a grounded conductor. Now in your electric field hockey lab, remember you had those magic bins that you drag stuff out of?
Mm-hmm.
That when you put them in there, you can't tell?
That's
well,
a grounded
those are
box.
grounded conducting boxes. They're not magic devices. It would be really awesome if we had this for gravity, because you could put something in there and not tell that and shield the entire universe from its gravitational pull. Of course, it doesn't work because there's no such thing as negative mass. But you can do this with electrical charge. You can shield the entire rest of the universe from it by putting inside a grounded conducting cavity. Okay, that does, you can mark it off.